Hello students, in this video we'll discuss confidence intervals. Suppose we're given samples x1 through xn of a distribution with parameter theta. That's a population parameter and that theta is unknown. That's unknown to us. Okay. And suppose we can use these samples to find a predictor for theta, right? So we can use an estimator. Suppose that theta, if theta hat is an estimator of theta, then we can construct a random interval, a 100 times 1 minus alpha % confidence interval is a random interval that has the following form that looks like theta hat, because that's my estimator based on the data, theta hat minus d, and then up to theta hat plus u, such that the probability that theta lies in that region, the probability that theta minus d less than or equal to theta less than or equal to theta plus u in that interval over there is equal to 1 minus alpha. Okay? And so I'll illustrate this by example. So what's a good example of this? So let's find I would like to find a 95%. So let's suppose that these, and of course theta is derived from these samples, right? So let's suppose we're given, here's an example of a confidence interval construction, given x1 through xn, etc., samples of a normal mu sigma squared distribution with sigma squared known. That's important that we know, in this case, we know what the variance is of these samples, okay? We do not know, with mu unknown though, so mu here is going to be unknown to us. We're going to try to estimate it. So mu is going to be unknown. And so to construct, say for example, a 95%, confidence interval for mu is constructed as follows, okay? We know that x bar, the sample mean, is normally distributed with mean mu and then variance sigma squared over n. That's our sample mean. And so what this tells me, therefore, is this tells me that x bar, for example, x bar minus mu over sigma, which is known, but mu is not, over the square root of n is a normal 0, 1 random variable, okay? Now what that means is now I can use facts from the standard normal distribution, for example. I know the probability, negative 1.96 less than x bar minus mu over sigma square root n less than 1.96. These come from the 95th distribution. In other words, what happens over here is if I look over here on a normal distribution, there's my normal distribution graph. If I pick this number over here, 1.96, and that number over there, negative 1.96, that's a symmetric thing, the area over here is 0.025, and the area over here is 0.025 by symmetry. So all total 95% of the mass lies between those 2 points. So this is going to be 0.95, or in other words, this is 100, and then 1 minus 0.05. So that's my alpha, that's my level alpha here in the problem, okay? That's my alpha is 0.05, okay? So alpha is typically given to us. And so now what I can do is I can say, great, well, this is a 95%, this interval over here, this random interval is a 95% confident interval. If I rearrange this inequality, what are we going to get? So we rearrange this. If I multiply by sigma squared over root n to both sides and then solve for mu, what we see is mu, the probability that mu is between x bar minus 1.96 sigma over root n less than or equal to, or just, I guess, just strictly less than, mu less than x bar plus 1.96 sigma over root n is equal to 0.95. We have a 95% confidence interval. We can see this interval is random because it depends on these random variables. So oftentimes you'll see this written in the following way. You'll see the confidence interval written as x bar plus or minus 1.96 sigma over root n. There, use a shorthand notation, say you're either above this or beyond this. Now, for example, I could have desymmetrized this, and I could have actually shifted this over a little bit and then done two different values. I could have maybe shifted this over a little bit, just a little bit to the right, and that a little bit over to the left. And by shifting this either direction, I can get other 95% confidence intervals for the mean. This is just the symmetric one that's used most frequently because we like to see sort of symmetric intervals. It's a lot nicer to visualize the symmetric intervals, especially when the distribution has an implicit symmetry in it. Thank you very much.